That's what matters. All right. This section, derivatives of inverse functions and logarithms. First off, what are inverse functions? How do you find them? What do they mean? How do you distinguish them from a regular function? If this is my regular function, how would I find the inverse function? Yes. First off, what's the symbol I use to differentiate? The -1 doesn't mean it's the 1 over function. It simply means it's the inverse of this function. The way you find the inverse function. First step, switch x and y. And solve for y. So we subtract 6. And then divide by 3, each term separately. Make sense? So what can we notice about these two functions with what we've been talking about for the last 4 weeks? Look at these two functions here. Okay, that's a better question. What have we been talking about for the last 4 weeks? The what? Mostly algebra and trig, yeah. It starts with a D, ends with derivative. Oh, very good. How'd you guess that? Derivatives. What do derivatives find? What do derivatives find? The slope. So the slope of our first function is what? The slope of our inverse function is what? So what do you notice about it's simply the reciprocal of it, or the flip of it? More so, we're going to take that one step further. Because up until now, all the slopes are non-zero. Why is that? What if we had a slope of 0? What does that graph look like? It's the x-axis. What's the slope of the inverse? It would be 1 over 0, which is undefined, which is a vertical line. We can't do that. So that's why we do all of our functions will always be functions with respect to some angle, some slope not equal 0. Right. So if they equal 0, then we can't do the inverse. So with that, here's our first equation that we have to know. Because since we're dealing with inverses, we have to be able to take the derivative of an inverse. How do we do that? So this is what we know. If M is the slope of y equals f of x at some point, or any point, which has to be continuous, a f of a if m is the slope of this, then that has to be true. No, I'm jumping ahead. If m inverse is the slope of the inverse of f of x. So if the function f of x has a point a f of a, what would the point of the inverse be? Because remember, you switch x and y to find the inverse. Then the slope is equal to 1 over the inverse of a, the derivative of a. Remember, how do we just saw that a second ago with our two slopes? The slope of a regular function and the slope of the inverse are simply just reciprocals of each other. Now I'm going to convert these. If b is equal to f of a, then the inverse function of b is equal to the inverse function of f of a. And what does that equal? The inverse function of the function is equal to what? Not 1, a. It equals the operation itself, right? If that's true, then the derivative of our inverse at b the derivative of the inverse has to be derivative of the 1 over f of a, which becomes the inverse of a. No, inverse of b, I'm sorry. Why is that? If b equals f of a, then the inverse of b equals the inverse of the function of f of a, which is 8. So the derivative of the inverse at b is 1 over f of a. How do I go from here to here? Very good. Because of here, if b equals f of a, then the inverse of b is equal to the inverse of f of a, which is a. So A is equal to the inverse of f of B. Very good. So that's where that comes from. Which tells us what? If we're going to take a derivative of an inverse function, what do we need to do? We have to take the derivative. We have to find the derivative of the original function and place the inverse function inside there. It's pretty much substitution. Let's look at an example here. Let me find the first example. There. It's pretty much just plug and play here. Given the function f of x equals x squared, where x is greater than 0, and its inverse, what would its inverse be? Square root of x. So remember, the formula we just had, we're looking for the derivative of the inverse. It's equal 1 over f. Which we can use x's now if we want. So the inverse function there, we put x value in here also. So what do we need to take this derivative? So to find the derivative of the inverse, we need to find f prime. What is f prime? 2x. So it's going to be 2 whatever x is. Our x is what? The inverse function of x is the square root of x. That's all it says. Because now, to take the inverse function, all you do is take the derivative of the original function and place the inverse function inside there in place of x. That's all it's telling us in 18 pages. Well, let's test it. If f inverse of x was the square root of x, how would we take the derivative of that the old-fashioned way? First off, make that a power of 1/2. Take the derivative of it, so the power comes down. Subtract 1, so it makes it negative 1/2. Makes it 1 over 2x to the power 1/2, which is 1 over 2 radical x. So, why do we have to know this new method of doing it? Look how many steps involved in this. In this one, if we have our inverse function, all we got to do is find the derivative of our original function. Anywhere we see an x, plug that in there. And we're done. So what happens when x is 4? That's another example. Let f of x equal x cubed minus 2 for all x's greater than 0. Find the derivative of the inverse at x equals 6. Let's do it two ways. One, without using the formula for what we just found, and two, using the formula we just found. So what would be our first way without deriving or using our formula we just learned? With the basic definition. We know f of x is x cubed minus 2. What's the first derivative? 3x squared. Do we have an x value that you can use yet? Remember, this is the x value at the inverse. What would it be here? With this one, what would it be? This would be my y value because x and y switch. So if it says for my inverse, this is my x value, that means for my original value, it's my answer. So what does x have to be to equal 6? X cubed minus 2 equals 6. Add 2 to both sides. X cubed equals 8. Cube root of both sides, so x equals 2. So we have to first find our x value, because if it gave us an x value for our inverse, we got to find out what made it 6. So let's look at our derivative. When x is 2, what is our first derivative? 12. So that means the derivative of the inverse would be what? What does this 12 represent? The slope. So what would the slope of the inverse function be? There you're done. That's without using our formula. Now, how do we solve it using the formula we just learned? Which is the derivative of the inverse is equal to 1, the derivative of the original function, times the inverse of the function. So we have to first calculate what is the inverse. Since f of x is equal to y is equal to x cubed minus 2, we got to find the f inverse. So switch x and y and solve for y. X plus 2 equals y cubed. Y is equal to the cube root of x plus 2. This is my inverse. What x value do we put in here? 6. Because this is the inverse, so we put the x equals 6, which is the y value of our original one. So we have the cube root of 6 plus 2 equals 2. So that means, and we also have to find the derivative. The derivative of our original function is 3x squared. So we have 3 in place of x, I put the inverse function. I plug in 6 inside there. So this gives me 1 over 3, 2 squared, 3 times 4, which is the derivative of my inverse. The hardest part about this is trying to keep the x and y values of the original function, and the yx values of the inverse function in check. So far, so good. Where else can we use this formula? What other inverses do you know? Do we know that are very popular in science technology? Natural logs, natural log functions. Because you see it everywhere. The E function is used in any biological study, how things increase, decrease in growth. So if f of x equals e to the power x, the inverse would be ln of x. They're inverses of each other. How do you test? I should have asked this sooner. How do you test if it's a true inverse? And it equals what? Yeah.
A number for x, your y should be what you get the inverse in the other function.
One more time.
So I think it's 5, right? And then it spits out 4. Then the inverse of it, if you put in 4, it should spit out.
Well, yeah, that's what's why. But to a test that won't happen because x and y and x they switch each other. But a true function is a composition function, the f of g function. If you do the composition, it should equal x. Because inverse functions are symmetric about the line y equals x. So if I put them composite together, then it should equal x. And it has to work both ways. The composite of the inverse function of my f of x function should equal x. That's a test. So let's say our function is e to the power x. What is its derivative? E to the power x. What is its inverse? ln x. So we can use what we just learned we can take this because what we're looking for is our derivative of our inverse. There's our f of x. What is the derivative of ln x? Remember what it was? Or do we ever talk about that? Is that 1 over x? Yeah. This is the proof of it. So since the inverse function is ln x, we use this. So the f prime is e to the power x. According to this, in place of x, I put the inverse function. The inverse function is ln x. What is the value for e to the power ln x? X. The same thing as if I took the ln of e to the power x, it would also be x, because they're inverses. They have to give you the same answer. So that's using our formula. Is there another way we could derive it? Using what we've been talking about from algebra? So we know that the derivative of our inverse function is 1 over x. Okay, so let's start off with what we know already. What we started off with. Here's the same example. If y equals ln x, let's find the first derivative. We can't just take the first derivative, because if we take a derivative, then we know what the answer is already. But what would you do here first? Try to get x by itself. What would you do first? What's that? How? No. You have to do something algebraic first. How do we get rid of the x from the ln? How? What's the inverse of ln? E. So if we take the e of both sides, is that what you said earlier? Oh, that's delogging? Oh, that's I never heard that one before. Oh no, this is calculus. So if we do this, now we can take the derivative of both sides. The derivative of e to the y and the derivative of e ln x. What is e ln x? That's just x. So the derivative of e to the power y. E to the y. What else? dy dx. Because whenever you take a derivative of y, you have to put dy dx after it. What's the derivative of x? 1.
Sure.
Yes.
Does that dy over dx be in the exponent or still just
No,
out?
no. This is multiplication. This is the product of it.
Okay.
What that was a chain rule. Take the derivative of this times the derivative of the exponent. Now we solve for dy dx. Divide both sides by e to the y. So dy dx is equal to 1 over e to the y. What is e to the y? Well, what is y? Y is ln x. So dy dx is equal to 1 over e to the ln x, which is dy dx 1 over x. Same thing. So we can go with it either direction we want to. So this was the whole thing we used to find the derivative of ln x. What if ln x, what if it's a function? What if y equals ln u, where u is a function of x? What would the first derivative be there? 1 over u, whatever that is, times du dx, the derivative of that. I'll look for an example. So y equals ln 2x. Find y prime. This is the u part. So if u equals 2x, what is u prime? 2. So what's the derivative of ln? Ln u is 1 over u, which is 1 over 2x, times the derivative of u, which is 2. The 2's cancel. The derivative is 1 over x. How about that one? What's the first derivative? So the derivative of ln is 1 over whatever that is, times the derivative of that, which is 2x. So the first derivative equals to 2x over x squared plus 3. Pretty easy. Okay, now back to algebra. Y equals ln absolute value of x. We talked about it some time ago, but does anybody remember the derivative of absolute value of x? How would you write the absolute value of x? in an algebraic formula. What is the purpose? What does absolute value do? Make it positive. In other words, it strips the negative. So the easiest way to strip a negative is if you take a number and if you square it, what happens to that number? It becomes positive. How do you bring it back down to normal? Square root it. So that's the formula for an absolute value. And no, unlike algebra, you can't say, I'm just going to strip that and make it first derivative is 1. Woohoo! No. Although the first derivative is 1 on half of it, it's -1 on the other half. It's positive -1. So when you take the derivative of this, you have to use a chain rule. Times the derivative of the inside, which is 2x. The 2's cancel. So we have x on top and x squared to the power 1/2. X squared. Power 1/2 means a square root. And like we just determined up here, square root of x squared is the absolute value of x. So the derivative of absolute value of x is x over absolute value of x. That side note was important because for us to find our derivative, what's the derivative of ln? What's that? 1 over. 1 over absolute value of x. It's 1 over u. Times the derivative of this is x over absolute value of x. Absolute value of x times absolute value of x. Do we really need the absolute values anymore if you square it? No. So you have, which becomes 1 over x. So you see, ln is a pretty boring function. Pretty much it equals 1 over x no matter what you do. Yes. This one? Let's see. X squared means what? I'm gonna hold off on that good question thing. No, it's a fair question. It's a very fair question. It's like you're now thinking you're thinking of higher level stuff. Yeah, this is the algebra stuff. That's supposed to be that simple.
Sir,
Yes.
so would you say the ln rule, finding the derivative of ln is sort of like the chain rule, where basically you're now flipping the reciprocal times the original self?
Yes. Yes. Because that's exactly what it is. It's the lnu is 1 over u du. So you take the derivative of the outside. Yes, you can look at it that way. Yes.
Okay, thank you.
Example 4. A line with slope m passes through the origin, which is 0, 0. And is tangent to the graph of the function f of x equals ln x, what is the value of m? Let's look what they're trying to tell us. A line passing through the origin, a line with slope m passing through the origin, we go through 0, 0, is tangent to the graph f of x, y equals ln x. What does the graph of ln x look like? What quadrants is it in? First and fourth. Crossing the x-axis where? Because remember, the exponential function crosses at 1, so the logarithmic function crosses at x equals 1. So there's a line going through here that touches the graph at one point here. Do we know what that value is? Do we know what that location is, where it touches? Well, we can figure it out. It's some value a. And what would be the y value at that point? Ln of a. Because the function itself is ln x. So we have two things to compare. We have the slope of this line and the slope of this curve. So what's the slope of this line? We have f of x equals ln x. How do I find the slope of that curve? First derivative, which is 1 over x. So the slope at that point would be what? Very good. So the slope at a would be 1 over a. So that's with the curve. What about this linear equation here? So the slope of this is 1 over a. What's the slope of this line? What do you need to find the slope of a line? 2 points. We have that point, and we have this point. Against the algebra rules. So to find the slope, we need to know y2 minus y1, x2 minus x1. And we have 2 points. We have a point at 0, 0, and we have a point at a, ln a. So ln a minus 0 over a minus 0. So the slope of the line is equal to ln A over A. And the other one, the slope was the first derivative, which was 1 over A. Set them equal to 0. I'm going to set them equal to each other, not 0. So we have ln A over A equals 1 over A. Since we have the same denominator, what happens? The numerators have to be equal.
Why do we set them equal to each other?
Because that's where they intersect.
Okay.
Because at this point, they have the same slope. Now we're solving for A, so we take the E of both sides. So get rid of the ln. The E of ln A is A. E of 1 is E. We just found out what the A value was. So the slope is 1 over A, which is 1 over E at that point. So that was a derivative for our ln functions, natural logs. What about if it's not natural log? Of A to the power X and log A to the power X, or A to the power U and log A to the U. For this section, we have to know the comparison. Where did A come from? So A to the power X can be written as what? No. Basically, we know how to do with E, right? So can we write A in a function of E? What would the power, if we had that, what would we get? Would they be equal? So this one can be E X ln A. So if whenever we have a base A other than E or anything else we know, we can rewrite it as E to the power X ln A. Why is it X ln A from this? How do I go from this to this? Very good. If you have an exponent, it becomes a coefficient. Right. Again, where do we learn this? Algebra. So algebra is going to be the kiss of death for us. So where's the example? Well, we haven't done derivatives yet. So if we took the derivative of these, because we're looking for the derivative of the basic function, then we'll expand it to a function of u. So the derivative of a to the power x dx. So what's the derivative of e to the power x ln a? What rule are we going to use here? Chain rule. Chain's a safe bet. This yell chain will be 90% of the time correct. So the derivative of e to the power x ln a is what? E x ln a times the derivative of the numerator, the exponent, I mean. What is the derivative of the exponent? Because you're taking it with respect to x. Ln a is a constant. So the derivative of x is 1. So now put this thing back in terms of a. What is x e to the power x ln a? Remember up here, a of x equals e x ln a. So this goes back to being a to the power x. So this is our derivative of any base a other than e. So what would it be if we had a to the power u? It would be the same thing. It'd be a to the power x ln a times du dx. Sorry, and I use a. It's u, not x. So derivative of a to the power u is a to the power u ln a times du dx. Let's look at some examples. Find the derivatives. If y is equal to 3x ln 3, what's the first derivative? Put our formulas down. So dax dx is ax ln a. dau dx is au ln a u prime. So does this one match our first or second formula? Our first one, because we have a is 3x. So the derivative, how would I find the derivative? Is it a chain rule? Is it product rule? Is it? This is a constant. It would be a product if this was a function of x, but this is a constant, so I could bring it out in front. So what's the derivative of 3x? 3x ln 3. X is 3, a is 3, x. I shouldn't have put that in there originally, but oh well, since I did. So it becomes 3 to the power x ln 3 squared. Ln 3 times ln 3 is ln 3 squared. B, y is equal to 3 to the power negative x. What's my first derivative? Which formula we're going to use? So we could look at u, the second one. Okay, so our u is negative x. The derivative of u is negative 1. So you have a to the power u ln a, which is ln 3, times negative 1. So it's negative 3, negative x ln 3. What's that? We can go back and rederive it. Because we needed the ln when we did the derivation of it. Right there. Because a of x is equal to that function from that conversion. A of x is e ln a. We take the derivative of e, we get that times ln a. So the derivative would be we're going to use a second since the exponent is a function. A to the power u, ln a, and the derivative of the exponent. So we're going to just write the equation down. Times ln of the base times the derivative of sine is cosine. All those together multiplied. Pretty straightforwardly boring. Not eventful because fortunately for us, great, because e's and ln's are super easy to deal with. Exponentials. This is also another important formula. When we deal with slopes, So we look at our function a to the power x. If we were to look at this function through a limit definition, remember the slope is the first derivative. So we'd use the slope formula when h goes to 0. Our conversion here as h goes to 0, it becomes our function ln a. It's a constant value. So we'll be using this whenever we have this limit value. What if we have a log base a instead of a natural log? Where a does not equal e. How do we find the derivative? How do we find the derivative of this? Believe it or not, it's easier than you think. Let's see if you can figure out how you would do it. With what we know from algebra. If I gave you this and I asked you to put in your calculator and tell me a number, could you do it? The answer should be yes. If you took algebra and pre-calculus. Because why can calculators not solve this? They're either log base 10 or log base e. So how do we go from log base 5 to either one of these? Very good. What is a change of base? If we're going to change it from log base a, then we can change it to log base 10, or we can do the natural log. Remember those? Because what we're looking for is the ratio, whether it's a log base 10 or log base e, it doesn't matter. It's the ratios will be the same values. So we convert a log base anything into that. So to find the derivative of this, I would change this to ln x over ln a. Now, to find the derivative, it's a lot easier. Do you have to use the quotient rule, the product rule, or what? Just the ln rule. Because log ln a is a constant. So that's 1 over ln a times ln x. What's the derivative of ln x? 1 over x. So the derivative would be 1 over x ln a. Simply by using the change of base formula. Now, instead of x, what if we had a function there. This was for ln log base a of x. This is log base a of x gives you this. Log base a of some function is equal to, remember, we have to ln u over ln a, 1 over ln a. The derivative of ln u is 1 over u du. So it's 1 over u ln a du dx. But it's the same concept. Any questions so far? Now, here's the beauty of what we've been doing. It will make life much easier for us. So if we had this, there's a derivative. X squared plus 1, x plus 3 to the power 1/2, x minus 1, where all of our x's are in Texas. No, greater than 1. Find the first derivative. Neither. You use none of those. How can you do that? By using the rules of logarithms. If I take the ln of both sides, I'm still looking for the first derivative. But before I do a derivative, let me rewrite what I have here. Ln y. What are the rules for multiplication and division in ln rules? The rules are these. If I have ln of x over y, what can I do? Ln x minus ln y. If I have ln of x times y, ln x times ln y. And then there's also the one we talked about earlier, ln x to the power n is equal to the n ln x. If you have an exponent, it becomes a coefficient. So we can now split up all these. So we have ln x squared plus 1 plus ln x plus 3 to the power 1/2 minus ln x minus 1. Basically, if it's on the bottom, it has a negative in front of it. If it's on top, it has a plus in front of it. Now we can take the derivative. What's the derivative of ln y? 1 over y dy dx. The derivative of the first one is 1 over x squared plus 1 times the derivative of x squared is 2x plus the coefficient comes out in front. So we take derivative of ln x plus 3 is 1 over x plus 3 times derivative of x is 1 minus 1 over x minus 1 times 1. So we have 1 over y dy dx, 2x over x squared plus 1 plus 1 over 2 x plus 3 minus 1 over x minus 1. Multiply both sides by y. So my derivative, dy over dx, is equal to y times this whole monstrosity plus 1 over 2 x plus 3 minus 1 over x minus 1 . You're not done yet. Because what is y? That. So now we get to write x squared plus 1 x plus 3 to the power 1/2 all over x minus 1 times this whole stuff. That's your first derivative. Again, algebra. It's all algebra and writing. Any questions about that? So you see the beauty of using LNs instead of trying to do the quotient rule, the product rule, the chain rule. I mean, think of how much time we'd spend doing that. We'd have to do the product rule here. The derivative of this one would require a chain rule. And then we have to use the whole thing. We have to use the quotient rule. So the ln function is a lot easier. This is less writing than what you would have normally done. So the general version of the power rule. Which means now, what was the power rule to begin with? And if our base was a function, So now we can keep that, but we can now make one further. Now we can use this. In place of x to the power n, we can write e n ln x. So we're no longer limited to real numbers or rational numbers. We can write any type, irrational, rational, complex numbers. We can do anything we want to, as now it fits in that domain. So now we're not restricted to anything. Let's look at one more example. X to the power x, where x is greater than 0. Differentiate it. When I say differentiate, what do I mean? Derivative. Take a derivative of it. I'll give you the clue what you're going to need to use. Top of the page. How can we use this to represent x to the power x? In place of n, I put an x. So here I have EU, where U is x ln x. Why do I need that? Because to find the derivative, I gotta take, this is e to the power u. So the derivative of e to the power u is 1 over u du. So what is the du, the derivative of u? I gotta use the product rule. F is x, g is ln x, f prime is 1, g prime is 1 over x. So my first derivative is 1 over x ln x times ln x plus x times 1 over x becomes 1. Oh, crikey. This is a derivative of what? Of ln, not e. So this one still should have been EU. This should have been EU. This should have been EU. So it's e x ln x times ln x plus 1. And what is x ln x? E to the power x ln x is x to the power x. So this becomes x to the power x ln x plus 1. There's my derivative. And that's the end of that section. Perfect timing because it took this entire period. End of section. I just put in there for my notes when I get ready to make copies of these for y'all. Any questions? So this whole section pretty much dealt with the same stuff, is derivatives of the e or the ln function.